Hi everyone, it's Japoo, and today we're going to be talking about how to evaluate limits algebraically. So just a reminder, if you would like to follow along to this video, I have linked the worksheet and its answer key in the description below. So today, as I mentioned, we are talking about evaluating limits algebraically, or how to do limits without having to take the derivative. Sometimes calculus classes in college cover this topic, and this is a valid strategy to find limits on the AP exam. However, most people find that there are better ways to find the limit, specifically using derivatives. So they prefer not to use this method that I'm about to talk about, although it is still good to know. If you are interested in learning about how to evaluate limits by taking the derivative, we do have a video talking about L'Hopital's rule, which is that method, on our channel, so feel free to check that out. So before we start the problems, I'm going to talk about the steps that we like to do when we are evaluating limits algebraically. The first thing that we want to do is plug in a number, or we're going to plug in A, excuse me. When we plug in A, if we get a number, that is our answer, and we're done. We only have to do step one. However, this is usually not the case. Usually when we plug in A, we're going to get 0 over 0. So if we get 0 over 0, the next step is to do something. I know that sounds a little vague, but the do something is based on whatever the problem calls for. What you have to do is do what you think best fits the problem. For example, you might see something that's factorable in the problem, and therefore your do something is going to be to factor a part of the problem. You could also expand part of the problem, combine fractions, or multiply by the conjugates. After you do step 2, whatever you've done should change the problem in some way so that you're able to cancel things, and then plug in A again to get an actual number instead of 0 over 0. So let's get started. Number 1, you can see that the top looks factorable, right? But before we get ahead of ourselves, of course we want to do step 1, plug in A, just to make sure that we don't have to just finish at number 1 and we don't have to do any extra work. Unfortunately, the limit does equal 0 over 0 here, so we are going to have to do something to this problem to get the correct answer. As I mentioned, the top looks factorable, right? So here we're going to factor the numerator in hopes that it will change the equation so that we can get the correct answer. When we factor the top, we're going to get x plus 2 times x minus 3 over x minus 3. And you'll see that we can actually cancel the x minus 3's, giving us a limit of x goes to 3 of x plus 2. So after we've canceled out those x minus 3's, we're left with x plus 2, right? And all we have to do is plug in A again. So plug in A to x, giving us 3 plus 2, which is equal to 5. And that's going to be our final answer. So moving on to number 2, if we plug into the top, we're going to get 2 squared minus 2 minus 6, which is equal to negative 4, and 2 minus 2, which is equal to 0. So since we have negative 4 over 0 as our answer, and that does not exist, we already have our answer and we don't need to go on to step 2. We're done here. So moving on to number 3, if we plug in 7 to the top, we're going to get 49 minus 49, and at the bottom, 7 minus 9 is negative 2. 0 over negative 2 equals 0. Again, all we had to do in number 2 and number 3 was plug in A, and we got a number. We got our answer. We did not get 0 over 0, and therefore we did not have to go to step 2 and do something. So it is nice when that happens, although I will warn you that that is usually not the case because they are going to give you probably more difficult limit problems in your classes and on the AP exams, but it is still good to plug in a just in case, so you don't have to do any extra work. So number 4, if we look at the numerator, we see that we have h minus 3 squared, right? And that's something that we can expand. Oh, I forgot to mention this, but if you do plug in 0 to the h's, you're going to get 0 over 0, which means that we have to do step 2. We have to do something. And as I mentioned, h minus 3 squared looks expandable. We can expand that. So that's what we're going to do. That's our step 2. So when we expand h minus 3 squared, we get, on the numerator, h squared minus 6h plus 9 minus 9 over h. Those 9's cancel, because 9 minus 9 is 0, which leaves us with h squared minus 6h over h. And I'm actually going to rewrite that by taking 1h out of the numerator, giving us h times h minus 6. So I took 1h out of h squared and 1h out of 6h, and that gave us h minus 6 times h. We can cancel the singular h out to get an answer of h minus 6. And then if we plug in 0 to our h, we're going to get negative 6. And that's our answer. Moving on to number 5. Unfortunately, it is a little bit cut off, but let's see. Okay, ignore number 6 for now, and I'll talk about it. Okay, I'll just talk about it. But for number 5, the bottom of our equation, of our limit, is factorable. We can actually do the sum of cubes formula for the bottom to factor that out. And what we're going to get is x plus 2 over x plus 2 times x squared minus 2x plus 4. Once we have that, we can actually cancel out the x plus 2's to give us 1 over x squared minus 2x plus 4. If we plug in negative 2 to our x's, we're going to get 1 over 4 plus 4 plus 4. Because negative 2 squared is 4, and minus sign 2, negative 2, times negative 2 is also 4, and then there's 4 at the end. So that's going to give us 1 over 12 as our answer. Number 6, we have a similar situation. After we plugged in negative 5, we got 0 over 0. So we're going to have to combine fractions as our second step. So we're going to combine fractions by finding a common denominator, and that common denominator is going to be 5x. So that's going to give us x over 5x plus 5 over 5x in the numerator, which equals x plus 5 over 5x, right? That means that we can cancel out the x plus 5 and the 5 plus x, because when you're dividing fractions, you multiply by the reciprocal. Once we cancel those two things out, we're going to get 1 over 5x. And if we plug in negative 5 to x, we're going to get 1 over negative 25 as our answer. So then, moving on to number 7. First, we're just going to rewrite number 7 to get rid of those negative exponents. So what we're going to do is have 1 over 4 plus h minus 1 over 4 over h. Since we moved the 4 plus h and the 4 to the denominator to get rid of the negative 1 exponents. Once we have that, we're going to want to combine our fractions, right? And our common denominator is going to be 4 times 4 plus h. So that's going to equal, move myself up a little bit, that's going to equal 4 over 4 times 4 plus h minus 4 plus h over 4 times 4 plus h. Watch that subtraction sign. You don't want to get yourself into any trouble because you forgot to carry a negative. Once we have that, and that's all over h, once we have that, we can actually go ahead and cancel out the 4's. Since 4 minus, in parentheses, 4 plus h is the same as 4 minus 4 minus h. So that means that it's 0 minus h over h. 0 minus h over 4 times 4 plus h over h. Excuse me. Don't forget your denominator for your top fraction. So after that, after we've taken out those two 4's and made them 0, we're going to have negative h over 4 times 4 plus h over h. And we can cancel out those h's since we're multiplying by the reciprocal of the fraction when we're dividing it. So it's basically negative h over 4 times 4 plus h times 1 over h. So now we're going to have a negative 1 over 4 times 4 plus h. And if we plug in 0 for h, we're going to get negative 1 over 4 times 4, which is equal to negative 16. All right, moving on to the next page. So far we've had examples where we had to factor part of the limit, we've had to expand part of the limit, and we've also had to combine fractions in the limit. And now we're going to be multiplying by the conjugate of the limit to get our correct answer. So if you plug in 7 for x, you're going to get 0 over 0, which means that we're going to have to do something to our equation. It's pretty clear in number 8 that we are going to have to multiply by the conjugate of the square root of the numerator at the top. So basically, when you have a square root, you're going to multiply by the conjugate of whatever part the square root is in. So if the square root was in the denominator, then we'd multiply the denominator by the conjugate. So what we're going to have, our conjugate in this case, is going to be x plus 2 square root of x plus 2 plus 3. So the x plus 2 doesn't change at all. The only thing that changes is the thing outside of the square root that's in the same place as the square root. So everything since the square root is in the numerator in this case, everything in the numerator is multiplied by its conjugate. And that's why we're switching the negative 3 to positive 3. So once we do that, on the top, we're going to get x plus 2 minus 9, since the square roots cancel each other out. And then on the bottom, we're going to get x minus 7 times square root of x plus 2 plus 3. So we've gotten rid of the square root in the numerator. And if we look at our numerator now, we can see that we can simplify it to x minus 7, right? Which is also in our denominator. So we're actually able to cancel out the x minus 7's. Once we do that, we're going to have 1 over square root x plus 2 plus 3 outside of the square root. And if we plug in 7, we're going to get 1 over square root of 7 plus 2, so square root of 9, which is 3, plus 3. And that's going to give us an answer of 1 over 6. Moving on to number 9, we're going to do the same thing that we did in number 8. Since after we plug in 9 to all of the x's, we get 0 over 0, we're going to move on to step 2. And in this case, we're going to multiply by the conjugate. So we're multiplying by square root of x plus 3. And I accidentally wrote both of the 3's inside of the square root, but here I correct my mistake. The 3 should be outside of the square root. It should be square root of x, like by itself, and then plus 3. And the reason we're multiplying both the top and the bottom by the conjugate is because technically we're multiplying by 1 over 1, right? Square root of x plus 3 over square root of x plus 3 is equal to 1. So that's why we're able to multiply by the conjugate. And we're only able to multiply the numerator by the conjugate if we also multiply the denominator by it. But anyway, after we multiply the top by the conjugate, we're going to get x minus 9 over x minus 9 times square root of x plus 3. Keep in mind, in this problem, whenever I'm saying square root of x plus 3, the 3 is not in the square root. So it's going to look something like this. And then we're going to cancel out those x minus 9's, which gives us 1 over square root of x plus 3. And if we plug in 9 for our x, we're going to get 1 over square root of 9, which is 3 plus 3. And that's going to equal 1 over 6. Moving on to number 10, we're going to first combine the fractions. So what we're going to do is we're going to have our common denominator is going to be 1 over x squared. And that works out in our favor because one of the denominators is already 1 over x squared. So we just have to multiply the other fraction by 1 plus x over 1 plus x. That gives us 1 plus x over 1 minus x squared minus 2 over 1 minus x squared. Once we have that, we can combine the numerators. So we get x minus 1 over 1 minus x squared. And if we look at the denominator, we see that we can actually factor that because 1 minus x squared is equal to negative, in parentheses, x squared minus 1. And if we factor x squared minus 1, we're going to get x minus 1 times x plus 1. So our final denominator is going to be x minus 1 over negative times, or in parentheses, x minus 1 times x plus 1. And we can cancel out those x minus 1's. Once we do that, we're going to have 1 over negative, in parentheses, x plus 1. And if we plug in 1 to that x, we're going to get 1 over negative, in parentheses, 1 plus 1, which is 2. So we're going to get negative 1/2. All right, so these next two problems involve absolute values. And I'm not going to go super in-depth about absolute values in limits because we do have another video that talks about limits involving absolute values. So if you're interested in learning more about that or you're confused by these two problems in my brief explanation of it, feel free to go check that video out. So number 11, if we look closely at the problem, we can see that the limit is going to -1 and then there's that like minus sign after the -1. That means that the limit is coming from the left in this function. Since absolute values are piecewise functions, there's going to be two kind of parts to it. So we're going to deal with the one that's coming from the left, which is the negative side of the piecewise function. So that means that our limit is going to equal negative, in parentheses, x plus 1 over x plus 1. So that's how you get rid of the absolute value in this case. Since we're told which side the limit is coming from, we know which portion of the piecewise function we need to choose for the absolute value. Since our options are x plus 1 and negative in parentheses x plus 1, we know that since it's coming from the left, it's coming from the negative side. So we're going to choose negative in parentheses x plus 1 over x plus 1. We can cancel those x plus 1's out to get negative 1. Number 12 is a little more complicated because we're not told which side the function is coming from. We're actually just finding what the entirety of the function's limit is. So that means that we're going to first find the limit of the right side. So we're going to find the limit of x going to 2 with a little plus sign after it. And then we're going to find the other side. So this side of the absolute value is going to be x minus 2 over x minus 2. There's no negative sign since we're on the right side, on the positive side. That's equal to 1. Then we're going to find the limit of the left side of the absolute value piecewise function, or the negative side. That's going to equal negative in parentheses x minus 2 over x minus 2. And if we cancel those x minus 2's out, we are going to get a negative 1. Since 1 and negative 1 do not equal each other, the answer to this problem is does not exist. This limit does not exist. If the limit of the right portion, the limit of the left portion had equaled each other, then the limit would exist. But in this case, it does not. Okay, number 13 looks a little bit complicated, but what you have to do is recognize that e to the 2t is equal to, in parentheses, et squared. So we can factor this. We're going to factor this as e to the t minus 1 times e to the t plus 1. Again, e to the 2t is equal to e to the t, all of that squared. It's funny that it's et like the alien, but the denominator is going to be et minus 1. We cancel out the et's minus 1, and then we get e to the t plus 1. Yeah, I keep trying to say et, but it's e to the t power. So then we're going to plug in 0 for t. E to the 0 power is equal to 1 because anything to the power of 0 is equal to 1. So that means that we're going to have 1 plus 1. And that's going to be equal to 2. So moving on to number 14, here we're going to have to remember our trig rules because we're going to try and change cosecant and cotangent into sine and cosine. So cosecant is equal to 1 over sine x, and cotangent is equal to cosine x over sine x. So cosecant x over cotangent x is going to be equal to 1 over sine x over cosine x over sine x. So it's going to look like that. Since we're dividing fractions, we're basically multiplying by the reciprocal of the second fraction, right? So we can cancel out both of the sine x's. Once we cancel out the sine x's, we're going to get 1 over cosine x. Since 1 over cosine, well, since cosine of 0 is equal to 1, 1 over cosine 0 is going to be equal to 1 too, right? So that means that our answer is just going to equal 1. So that's it for this worksheet. And eventually, if you keep watching all of our calculus videos, you will learn ways to solve limits with derivatives, which a lot of people think is easier. So most people do evaluate limits using derivatives. 2 videos that I can think of off the top of my head where we do talk about limits and derivatives is definition of derivatives and L'Hopital's rule. So if you want to learn more about that, please check those videos out on our channel. If this video helped you out in any way and you enjoyed it, please give it a like and subscribe to our channel for more calculus videos like this. Thanks.